All right, hello everyone. Here we're going to continue talking about combined gas law. Before we run into actual calculation, there are a couple of things, simple things I want not re-clarifying with you, but just to readdress with you guys a little bit. Okay, so basically we all know that the combined gas law look like this. PV equals to nRT, where R is a pi constant, and we're strictly to be using ATM, liters, mole, and Kelvin for temperature. Anyway, we have a very restricted rule about units we need to use here. Now, if we rearrange this into, depends on what you're trying to solve. You can solve P here, you can solve V here, you can solve N, you can solve T. But anyway, you need to know all other things to solve the last one. So that's the basic usage of this formula. Now there's some other situations, okay. As you can imagine, okay, 4 variables: pressure, volume, mole, and temperature. 3 of them are a little bit different from the other one, which is mole. Mole is the quantity of the gas, whereas pressure, volume, temperature are more like the condition of the gas. Let's say most of the time we're dealing with a constant amount of gas. There's no leaking, no putting more gas in. So in other words, let's say the mole is not changing, given that R is not changing either. So you can imagine the N times R is going to be a constant. So let's say we're going to isolate NR, 2 of this, moving T over. So NR equals to PV over T. So what we're trying to solve in the next, a few minutes is going to be, what if we have conditions, pressure, volume, temperature, one or more than one, changing only. There's no mole changing. So NR basically remain as a constant, the products of NR. Now we can use the same concept from Boyle's or Charles' law. Okay, we can develop into something like this. If nR remains a constant, we're only changing pressure, volume, or temperature, then we should have P1 V1 over T1 equals to P2 V2 over T2. So even though it doesn't look like, it looks very different, but I want you to keep in mind this is a derivative from the original. The original formula is still here. This is a formula doesn't look like original one, but it's really derivatized from original one under the condition that N is not changing. And changing condition only. Okay, now let's take a look at this formula. Okay, if we happen to have temperature not changing either, so T1 equals T2, so basically these two can be canceled out. See, this is Boyle's law. Okay, now if we have pressure to be constant, P1 and P2 are the same, then you would be able to cancel P1 and P2. So you would have V1 over T1 equals V2 over T2. That's Charles' law. So you see, all of those are Boyle's law, Charles' law, or even possibly Avogadro's law. It's just a branch of this main formula. Okay, so next couple example is if we have a changing condition only situation, how we're going to utilize this formula to solve problem. Okay, so let's take a look at a couple of problems here. As usual, I'm going to work out one of the problem, and then you guys can feel free to pause the video in the middle and then see if you can try work out the other one. But of course, I'm going to work out both of the problems, just so you can compare your work with. So you can see, since we're looking at quite a few numbers, so most of the changing condition problems are relatively long, lengthy, and so it becomes more important to write out numbers along the way. Okay, so let's say the first one. A sample of di-boron gas P2H6. Again, over and over, we'll talk about this. You don't have to worry about what kind of gas this is if you're just trying to solve a gas law problem, unless you're dealing with molecular weight. Most of the time, we're not. A substance that bursts into flames when exposed to air has a pressure. Okay, so here's the first number we need to pay attention. A pressure of 0.454 atm. That's a pressure. At the temperature of -15, temperature is -15. So this is clearly telling you this is the pressure at this temperature. So you can give them the same substrate number label in here. And the volume 3.48. So the volume is going to be 3.48. So this is the parameters under the same condition. P1, V1, V1, T1, V1. If conditions are changed, okay, so this is a question that's very generous, telling you this is changing conditions. Sometimes other question may not tell you this, but you just have to read it out, okay. So that the pressure is 0.616. So after changing condition, of course, your pressure is going to be different, okay. So you're going to give a different number down here, 0.616 atm. And the volume is 3.06, V2 is 3.07 L. What will be the new temperature? So T2 is what you're looking for. So this is, you have P1 V1, T1 V1, P2 V2. You're only missing one, which is T2. Okay. So the formula we're going to use here is going to be P1 V1 over T1 equals to P2 V2 over T2. Okay, we're trying to solve T2. Now keep in mind, okay, the units here though. Since we're not using the R value here, so this R value here is useless basically. For that reason, the units of pressure and the volume can be a little bit flexible. Okay, but the temperature has to be Kelvin. So you cannot use Celsius degree here for either T1 or T2. It has to be in Kelvin. For pressure, you can have atm, you can have torr, millimeter mercury. For volume, you can have liters, gallon. It doesn't matter. For temperature, it has to be in Kelvin. Okay. Keep in mind, you're only going to be restricted to atm, liters, Kelvin if you're using the R value. Here, we're not using the R value, so the pressure and volume are okay. Temperature is exception. Temperature has to be in Kelvin no matter what. Okay, whether you use R value or not. And of course, the T2 here, once you find it out, it's going to be Kelvin as well. Okay, so if you're trying to solve anything that's already at the bottom, the first thing usually I would suggest you to do is flip both sides upside down. You can't just solve something that's at the bottom. Okay, you have to flip upside down to make sure what you're trying to solve is on top before you do anything else. And then solve the algebra from here. Don't plug in numbers yet. Okay, so T2 is on this side. You want to move P2 V2 over by multiplying on the other side. So you're going to have, and then flip right to left. Okay, so you move T2 on the left by itself. On the other side of the equilibrium symbol, you're going to have T1, and then along with P2 V2, which was just moved over here, and divide by P1 V1, which they were there anyway. All right, so you can see there are 5 numbers you're gonna plug in here, so make sure you plug in them carefully. Okay, T1 again has to be in Kelvin. P2 V2 0.616 atm. V2 is 3.07 liters. P1 V1, P1 is 0.454 atm times V1 is 3.48 liters. So you can see atm and atm cancel, liter cancel. You're gonna have a Kelvin only, and you still need to count number of sig figs of all of these numbers. And you have 3 or 4 of them, so you can have 3 sig figs for your answer, 309 Kelvin. Okay, so this is first problem. You can pause here, try the second problem. Now let's see the second problem here. It's basically the same concept, okay? Natural gas is often collected at a great depth of the ocean. Calculate the volume of natural gas at the sea level. So at sea level means you're given 1 atm, but it's the pressure. Temperature is 23.9 Celsius degree. Now you can almost immediately convert this into Kelvin by adding 273. Okay, that's a constant. Okay, this is the sea level condition. You are trying to find the volume of sea level. So in other words, let's say if this is P1 and this is T1, the V1 is not 25 liters. The V1 is what you're trying to calculate. Calculate the volume of natural gas under this condition. If it separates two conditions, if 25 liters, which is the V2 is 25 liters, of the gas is collected at 6,500 feet below. I'm not sure why this is here, but apparently in gas law calculation, the depth of the water is not important, okay? Below the surface, where the pressure is this and the temperature is this. So this 25 liters of gas were collected under this pressure at this temperature. So this 25 liters is collected under P2, which is 196 atm, and at this temperature, 1.6 Celsius, which is, without doing anything else, just put this into Kelvin first. So you have P1 V1, P2 V2, T2. You're solving V1 as usual. The formula here is going to be P1 V1 over T1 equals to P2 V2 over T2. You're trying to solve V1. You just need to move P1 divide by P1. So on the other side, you have divide by P1 as well. T1, you have to multiply by T1. And on the other side, you have to multiply by T1 as well. So let's rewrite this, okay? V1 equals to everything else canceled on this side. V1 has been isolated by itself. On the other side, you have P2, V2, T1 on top, and P1, T2 at the bottom. Now you just need to plug in all the numbers. P2 is 196.7 atm. V2 is 25 liters. And T1, I'm sorry, it's not T2. T1 is actually 296.9 Kelvin. P1 is 1 atm. And T2, last thing, is 274.6 Kelvin. And make sure you do the math correctly. Multiply 3 numbers on top, divide 2 numbers. Okay, if you're not sure how, okay, make sure you print the sides, both numbers on top and the bottom. Calculate 2 numbers first and then divide 2 numbers. And this is going to give you 3 sig figs at the end. 5,320 liters is the answer. Okay, alright, so this is the changing condition of combined gas law.